right? So it's kind of interesting, because just think of it this way: like I'm sitting in a room right now, the window's open. I'm actually kind of warm. Like my head is kind of warm. You can tell by the like the shine, the sheen on the dome, freshly shaved, of course. But yeah, it's a little bit of a glossy sheen. But my toes are frozen, right? And that's because the window's open. Yeah, I'm in the corner of a room. The ventilation is it's good. It's good enough to cool off the room, but not good enough to cool off my head, I guess. And also, I got the light of the computer and the iPad and every device in creation shining in my face. The TV part is self-inflicted. That's my problem. But I need some distraction in the background, otherwise I go insane. But there is this variable temperature throughout the room. All right. So that's a fourth dimension. Right? I have 3 dimensions already. The position within the room of the top of my head, for example, if I designate the lower corner behind me as 0, 0, 0, then I could say that my head is 2 feet along the x-axis, or they think about 5 feet along the z-axis, and if we're calling this the y-axis, maybe a foot. All right, so 2 by 1 by 5. All right, so I have 3 dimensions already accounted for. I can add in a 4th dimension by throwing in temperature, the temperature within the room. Now that temperature might be a function of time. Right? So let's say it was really toasty in here before, and then I opened the window and it started cooling off over time. Well, that temperature is a function of time. I'm up to 5 dimensions. All right. Now you could start getting into air pressure and things like that, and you can increase the number of variables and therefore increase the number of dimensions. But it's funny because you watch a sci-fi movie and they'll have you convinced that the 4th dimension is time, and it's that's the key to time travel. Well, I mean, yeah, that sounds great in theory, but I mean, there's so many. Any other variable beyond 3 physical dimensions is considered a leap into the 4th dimension. Right? The issue is it's hard to conceptualize that graphically. Right? They have different sorts of flow diagrams, but that's not really in the neighborhood of what we're going to be working on. But we can start looking at 3-dimensional renderings of 4-dimensional graphs and start to kind of make heads or tails of this. Linear algebra, I mean, if it's this is going to sound terrible. If it's taught the right way, should give you a good glimpse into the power of higher dimensions. Right? If it's more of a focus on, okay, now reduce this matrix, now reduce that matrix, and it's like, oh, okay, well, another matrix, and you never really get into applications, then it could feel like it's just math for math's sake. It's fun too. But if you really want to get a sense of the power of it, applied mathematics, it really does a good job of that. That's when you start, getting the physics involved. It's pretty cool. All right. So anyway, triple integrals are going to get us into that neighborhood, right? Or at least start our journey into that neighborhood. So the objective, you should be able to compute triple integrals and use them to find volumes. Very, very astute, of course. But let me just draw you a quick diagram. I'll try my best. Every time I get a little bit better at it, but it by no means is perfect. Right? So if I start off with a single unit cube, and actually, it wouldn't even be really a unit cube. It would be a single cube that I'm using as the basis of this system. See, this is the dance that I'm going to have to do for like the next half hour while I try to get this to be like a vertical line. It's like, okay, yeah, why? And then I got to freehand this. My whole diagram is shot now. right? Because that's what's like, I needed that to be good. Now it's going to look terrible. Yeah, because now I got to freehand it. Ugh. All right. Put a hex on a whole thing. I'm just going to hang on to that. So this cube, obviously 3 dimensions. Now those 3 dimensions would normally be some change in X, change in Y, change in Z. Right? But if I want to minimize this so that its distance is infinitesimal in terms of the change in X, change in Y, change in Z, then capital delta X becomes lowercase delta X. And so we start to think of these as, well, we'll just pull it out on the side. Dx. Oh, I lost a little thing. Oh, I never put it in. That's why. Dx, dy, dz. You know, it really doesn't matter where you put them, obviously. I mean, as long as they're parallel to where they ought to be. So just bringing it back in. Let me get that in. Oh, too thick now. Perfect. All right. So what we're saying is that we're going to incrementally fill up this box using this little unit of cube. All right. So I'm going to build it along the x-axis. This is where it starts taking a walk on me. All right, so every one of those cubes built or extended out, or even overuse the term propagated outward in the x direction. Then each row corresponding with those little changes of x's. Now we filled up the required volume in terms of the x direction. All right, so now what we have to do is span that over so that we fill up the entire region in terms of, or based off of the infinitesimal change in y. Okay, we get to a point where it starts going a little bananas on me because it doesn't like what I'm doing. And it goes slower and slower and slower. Ah, I'm short 1. Son of a gun. Oh no. Well, this I can handle. All right, so now I've spanned it out along the y-axis, infinitesimal changes in y. And now all I have to do is duplicate this up the line. All right, so that's going to look pretty terrible when it's done, but it's the best I can do. So here we are. And you see now it's really overloading. Let's go with a nice. Oh no, that's hideous. Undo, undo. I think I'd rather just leave it like this. 20 minutes or so. Crash, crash, crash. I'm sure it's gonna. Oh. All right, I'm just going to paste in one more because I think we all get the idea. But I never like to leave a box half empty. I prefer it to be half full. Pretty close. And just like every piece of artwork that I've ever produced, it always looks better when you go really, really, really far away. And so what I'll do is I'll just do a little. And there we are. All right, so that's what's happening. We're filling up the space between the surface and the XY plane using little teeny tiny cubes. So that's all we're going to be doing in a lot of cases. But what we can do on top of that is, because we're integrating with respect to X, Y, and Z, we can now incorporate an additional function. All right, that additional function could be density. It could be mass. It could be, well, probably density giving mass, but it could be temperature. It could be time. It could be a bunch of different things. We could parameterize it in terms of whatever we want. There's a bunch of different ways we can go. All right, so the first example here, use a triple integral to find the volume between the surface defined by the function below and the region given in the XY plane. All right, so this function, the Z function, or would-be Z function, if I solve it for Z, would be equal to 4 minus 2x plus y. All right, now if this were a double integral, what we would actually be doing is figuring out what the bounds would be in terms of x and y and integrating this. All right, what we're about to do is actually going to seem like it's an unnecessary step, just trying to make things more complicated than they need to be. But it's actually a very important step to be able to transition beyond 3 dimensions. All right. So they gave us some bounds. They gave us the bounds for x, for y. It's rectangular, which is great, which means the order of integration for the x and y is going to be interchangeable because it's rectangular base area. All right. But what we're going to do is we're going to set up a triple integral. Now we're going to find a triple integral of just one. dz, dy, dx, that's another x, dz, dx, dy, dz, or dy, dx, dz, it doesn't matter, all right? This is the standard way of doing it, and it also, it's necessary in this case that the z comes first because that's the only variable part of this, right? So the question becomes, well, really, why 1, right? And that actually confused me when I first saw this. Right? 1 dz dy dx. You think about what that means. This is saying 1. Oh, actually, I could even box in the whole thing. 1 schnitzel. I never remember. It's one infinitesimal cube. It's just because I say it all like New York like. So I end up not saying it the way it's spelled, and I always get confused on how it's supposed to be spelled. If I said infinitesimal, I think maybe I'd remember how to spell it right. Fortunately, this question didn't come up on the 4th grade spelling bee championship of Dutchess County. Otherwise, I wouldn't have won the whole thing. Okay, so I mean, no big deal. No big deal. So impressive. So this is one infinitesimal cube. So this is one of these teensy tiny cubes that make up this region. Right. So what I want to do is integrate all the different cubes based off of the different boundings or bounds. All right. So I would need to know the bounds in the z direction, the bounds in the x direction or the y direction or x direction interchangeably. All right. So for z, they're variable bounds, right? Because we're going between, it's the triple integral to find the volume between the surface defined by this function and this region in the xy plane. The xy plane happens when z is equal to 0. So my z bounds are actually going from 0 to 4 minus 2x plus y. My y bounds are going from -1 to 1. My x bounds are going from -1 to 1. Now, if you carry out this process, we're integrating 1 with respect to z. All right, so like think about what we're doing here. If we're integrating just this piece, there's really no way for me to box it in without making it look terrible, so I'll just do this. We're going to get z over the interval of 0 to 4 minus 2x plus y, which in turn is going to be, when you substitute in for z, 4 minus 2x plus y. All right, so this is really the same as saying the double integral over the interval of -1 to 1 of 4 minus 2x plus y dy dx. All right, so now when you really think about it, it's like, oh, well, isn't that where we started? The last topic. If I wanted to find the volume beneath the function z in terms of x and y, multivariable function, the surface between the xy plane and z equals whatever, what did I do? I just integrated, I used a double integral of whatever the z function was over the xy bounds. Right, so this is the step that leads to that. So it's actually kind of cool. It's like getting a prequel going. So the question is it always cubes and not rectangular prisms? If it is, why are Riemann sums double integrals done with rectangles? So what's actually happening is we're truncating the rectangles that are done using the Riemann sums. We're truncating the heights so that they have that infinitesimal height of dz, right? So you're still getting that rectangular look, except it's only max. I'm sorry, you're still getting, a rectangular look, and you're just cutting it off at a certain height, which is creating that cubic relationship, right? So the dz part where it was originally a z, if you kind of think about that, just going back, you would have some kind of function, like let's say you have some sort of surface. This is the only surface I'm capable of drawing freehand, as we've all come to experience. Not looking good. Not looking good. It's my z-axis. That moved on me. All right, so this is my z. If I'm saying that I'm looking for the volume captured underneath this with respect to first X and then Y, for example. Okay, so I'd be looking at something along the lines of, get a little rectangle here. So that would be my little dx going up z units. All right. So, I mean, terrible diagram, I know, but just at least that part of it should be okay. All right. It's going up z units. But what we're saying here is that no longer are we going up z units, we're truncating it so that we're only going up dz units. All right. So instead of going up y unit z units along y or along a dy, get that out of there, make it tiny. We're also truncating that. All right. And so what's happening is, my diagrams are never going to be good, but if we were to merge these together, because we're minimizing the dy, minimizing the dx, minimizing the dy, if we were to wrap these around so that they came together, so let me get red involved. So this would merge, you know, they'd be swinging in order to create a corner. Well, really, I guess it's just these two. Because that would actually do it. Then you'd still have that dz, which is the minimum possible vertical distance. If we have a minimized horizontal distance, quote unquote horizontal distance, in the direction of x and y, then they would be approaching the same infinitesimal distance, which would create a cube. Right. So it really is just a matter of just chopping off. It's sort of like you're chopping off the rectangle at the knees. All right. So it's more of a theoretical change, but it's still actually happening. One of these days I'll be able to draw it correctly. That'll actually help. So now we're at the point where what we can do is actually interpret using a Riemann approach, because that 4 minus 2x plus y is z, and that's being multiplied by the dy, and all of those rectangles are being integrated together. So really, if you think about it, it would have to be the case that they're equivalent in terms of the rectangles and those cubes, because all that's really happening is that we're building up based off of these little squares. We're building up to the height of the rectangle in each case. So dz is actually becoming the integration. I'm sorry, z is becoming the integration of all the little dz's. All right. So really, really kind of cool, but it's definitely mind-bending. Now, in terms of the solution, there's nothing new here at this point. So I have to integrate this with respect to y. So we're talking 4y minus 2xy plus 1/2 y squared over the interval of -1 to 1. Hopefully, I mean, I'm not trying to steer you towards hating rectangular coordinates, but let's just put it this way. I'm kind of trying to steer you towards an appreciation of polar cylindrical coordinates. Right? Because you even see stuff like this, and it's like, I know I can do it, I just don't want to. Right? So we're replacing all the y's with zeros. Oh, that's wonderful. Replacing all y's with ones, I should say. So, as in, it's correct to say that. 2x plus 1/2 minus -4 plus 2x plus 1/2, barring any mistakes, always possible. So we'll just run through with the negative. Boop, 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 boop. These are my new signs. All right, so the 1/2 and the negative 1/2 will cancel away. We're looking at 8 minus 2x. All right, and so then I would have to integrate that over the interval of -1 to 1. So -1 to 1, 8 minus 2x. Now we can go calculator just because we're looking for convenience. Always looking for convenience. Eight minus 2x dx 16. All right, so somehow this ended up, I mean, barring any mistake on my part, always possible, but barring any mistake, we actually ended up with a clean answer here. So it is possible that this is something that could have been done using a geometric rule, which would be a cool investigation, based on the fact that this part of it seems to be linear. I mean, it is a plane. The z equals 4 minus 2x plus y is the equation of a plane. So depending on what its orientation is, you might be able to get a length, width, and height out of that. In which case, you can figure it out from there. All right, so that's kind of cool. But like I was saying before, the triple integral is actually a nice method for us to figure out something like, for example, density. So you have, and here is really the textbooky sort of diagram. I prefer to go through it this way because I think I learned it better or started to understand it more once I saw animations that involved building outward from that single unit. It's kind of like understanding, a molecule based off of how the atoms are constructed. It just anything when you're thinking of its base component, right? And so it just helped me understand. So I figured it might help somebody. This diagram here is also kind of okay, but if you don't know what the length, widths, and heights represent, then it's kind of all over to begin with, all right? So, and there's your Riemannian interpretation of it, but that's kind of another story for another day. All right. So I'll read the little blurb here for you. Triple integral allows us to incorporate an additional dimension. All right. Typically, f of x, y, z is a function that represents the density within a space, depending on the coordinates within that space, right? In the physical sense. If we multiply density by volume, the result is mass. All right. That's the rho equals m over v. So if we solve for m or mass, we get rho times v. Right. So if we look at the triple integral of a density function, we could actually get the mass of an object having a certain volume, basically based off of its dimensions. Right. So it's a cool little application of it. Right. So now, this is actually, I mean, if you look at this example here, it's a function of x, y, z, which, it doesn't say anything about density, but it is a function of x, y, z over a bounded interval, right, in terms of x, y, z. And we have the Fubini's relationship that exists that tells us that if the base region is rectangular, then the order of integration is interchangeable for the x and y, but it also adds in that added dimension of z, all right? So if you look at the different permutations that you could have, if it's a cubic relationship, so not rectangular, but a cubic, not cubic as in power of 3, but cubic as in a cube, then you would also have an additional layer of variation, right? So if you just think back, I mean, this might be a blast from the past, but if we take, you can do 3 factorial, 3 times 2 times 1, results 6. This would be the six arrangements that you could have. All right. So, and that's because you have dx, dy, dz representing those three things being arranged. All right, so any of them can occupy the first position. Once one of them is placed, only two remain to occupy the second position. Once one of those two values are placed, then there's only one value left to occupy the third position. All right, so 3 times 2 times 1 gives you 6. All right, so this would actually be the sample space of the different ways in which you could have the interchanging integration orders. All right, so that only occurs if you're dealing with constant bounds. All right, those constant bounds create rectangular regions in the XY plane, in the YZ plane, and in the XZ plane. All right, so in those three planes, you have rectangular regions coming together to form something that's cubic in nature, or the most infinitesimal component would be cubic. All right. Oh, possibly. Let's take a look. Oh yeah, fun fact of the day. 2 minus 2 is 4. No, 2 minus 2 is 4. Oh, that's the dumbest thing I've ever said. And I think I'm not wrong about that.
You should still
negative 2 minus 2.
16 is still going to be the
is negative.
Yeah.
Jesus age Christmas. All right. So did it somehow come out to be the same thing?
Yeah, I did it by hand and it was the same.
Oh, okay. That's something. I'm just surprised by that. The fact that it came out the same way, even though it was the wrong coefficient. Huh. 8x minus 2x squared versus 8x minus x squared. Oh, because that's so weird. I'm just sorry. I'm just like I can't stop myself sometimes. So that one, so you got 8 minus 2, and then you'd have negative 8 plus or minus 2 again. All right, so minus, that's fine. But then 8 minus 2x gave you 8x minus x squared. Oh, it's because the x squares would cancel anyway. Okay. Yeah. Yeah, because power 2. Okay. I was just thrown off by that. That was so weird. / cool. It's the beauty of an even function, or at least that part of the key. All right, so for last problem, dz had to go first because z was a function of x and y. Exactly. Very good. Very good. So we have our different ways in which we can arrange dx, dy, dz. Now, we want to use that information strategically because, like we've seen before, sometimes it's easier to work with one variable first as opposed to another. But again, it only works if you're dealing with constant bounds. All right. So I'm looking at 4y e to the x sine of z. All right. And this is over the intervals of 0 to 1, -2 to 2, and 0 to pi. So I want to be thinking about which one is going to be easiest to work with first, easiest to work with last. I don't know. Based on what I'm seeing here, it doesn't look like any one of them is any more challenging to work with than any other. The one that requires the least amount of effort is the e to the x. Right, so maybe we crank that one out first. So over the interval of 0 to 1, I'd figure out the antiderivative with respect to x, which is going to give me the exact same thing because the antiderivative of e to the x is e to the x and everything else is treated as a constant multiple. So 4y e to the x sine of z over the interval, that's not a vertical line, over the interval of 0 to 1. Now, if I replace the the x with a 1, I'm looking at 4y e to the e times sine of z minus 4y e to the 0th is 1, so that's going to zap away times the sine of z. All right, so then next up, you start looking at, okay, convenience, what's going to be easier to work with. The trig function doesn't look that bad because everything else is going to stay put. All I'm going to do is replace the sine with a negative cosine. That's happening over for the z, it's happening from 0 to pi. Okay, so the antiderivative here is going to be negative 4y e to the cosine, or e, I keep wanting to say e to the e times cosine of z plus 4y cosine of z. And that's happening over the interval of 0 to pi. Now the evaluation part of it's kind of a pain. Maybe it would have been better to go with the y's first. I don't know. It, you know, it really didn't seem like it would be, but you never know. All right. So you go down a road, and then if it doesn't play out the way you want it to, you go down a different road. But cosine of pi and cosine of 0 are, you know, -1 and 1 respectively. So it, as far as computations are concerned, that's really not too terrible. So I'd replace with a pi first, the negative 4y e cosine of pi minus, plus 4y cosine of pi. Then from that, I would subtract off negative y e cosine of 0 plus 4y cosine of 0. All right. Cosine of pi's become -1s. So we're looking at 4ye minus 4y. Just do the little negative distributing here. I like to circle it so I don't lose track. Cosine of 0 is just going to become a 1, so plus 4ye minus 4y. That's going to be 8ye minus 8y. All right. Now the next layer here is integrating this with respect, well, the only thing left is y over the interval of -2 to 2. All right, so from -2 to 2, dy, now I go calculate it, right? Because I can. And it's going to have an e in the answer, so I'm expecting a disgusting decimal. That's all right. If I can try to figure out what that is equivalent to in terms of e, and that's fine. But if not, I'm just going to go with a decimal answer. And you can too. Oops. I don't know why I'm using y's here. It really doesn't matter. But oh, lovely. E minus 1 could factor out. Okay, well, it says 0. So. Well, I don't remember that being the answer, but I'm sure it can be. Let me just do it by hand real quick. Kind of defeats the purpose of strategically deciding which way to go, but I'm kind of doubting it. So 4 y squared e minus 4y squared over the interval of -2, 2. Oh yeah. Yeah, it would zero out. Because when I replace the y's with, yeah, if I replace the y's with either -2 or 2, it's going to be the same. So it should zero out. So the units here are dependent on whatever the units are for this. Right? So we don't know what the units are for that. So what we would say is units cubed times whatever the units are for the function of x, y, z. Right? Because that's bringing it into the fourth dimension. Right? So if this function f of x, y, z is in terms of let's say it's temperature, it's degrees Fahrenheit or something like that, then your units would be degrees Fahrenheit times cubic units. Right? So it's always whatever the units are for the given function multiplied by a given multivariable function in 3 dimensions, or in 3 variables, I should say, multiplied by the volume's units, whatever those are. So units cubed for that. Right? So since in this case we don't know what the units are for that function, we would just leave it unitless, because what could we put, All right. So let's see here. Yeah, got a couple minutes left. We might as well bang out the next one. Write the triple integral that would be used to find the volume contained by this function over the solid tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0. Right? So that's giving you the first octant, and x plus y plus z equals 1. Right? So what I would be looking for is specific bounds in terms of x, y, z, right? Because I know that, and we're looking at a triangular relationship. So that's the first kind of, we'll call it a red flag. But we are looking at something that's not going to be rectangular, right? So you got to be very careful about this, right? We do know that it's contained by the function that of 3 variables. So I'm not worried about that. That's not going to factor into the bounded region. That's just, like the equivalent to, like, let's say a volume. No, I'm sorry, not a volume, like a density or temperature or something like that. Some related but unrelated function. It's not related to the contained volume though. Right. So what we need is a triple integral that's going to represent the volume of this region. All right. So it's going to be a dx, dy, dz in some capacity. Now I do have a way of relating z to both x and y. All right. So we know that x plus y plus z is equal to 1. Which means that z is equal to 1 minus x minus y. All right. That portion of a plane that you're seeing, that is the z equals 1 minus x minus y, or x plus y plus z equals 1. All right. So we have that part of it. We just want to be thinking about where everything's starting and where everything is stopping. All right. So in terms of x and y, it looks like we have a linear set of bounds in the xy plane. So we look at it that way. In the xy plane, we would say x plus y plus 0 is equal to 1, in which case we would say y is equal to 1 minus x, or x plus y equals 1, however you want. All right. So I now have a relationship between y and x. All right. I can develop a relationship between everything. So these bounds, really, if you think about it, we're looking at the xz plane, which is y equals 0, as being a bound. All right. Because that kind of sets you up over here. Let me see if I can reasonably draw that in. You can do it like this. All right, so we kind of create a wall here. Then we create a wall over here based off of the fact that we're on the y-axis, which would mean that we're living in the YZ plane, which would be where x is equal to 0. Right? So this is the x equals 0. This is y equals 0. All right, so we already have some natural bounds there, right? But we want to restrict it even further. So we can restrict it based off of z, so that in addition to cutting it off from being part of the the negative realm for x and y, we're now also trimming it down so it's below, or it will be if we establish that we can go no further below than the xy plane, right? So the floor, right, which is z equals 0, right? All of which is given to us, right? So we have bounds for x, bounds for y, and we have a natural bound for z, right? So we're in pretty good shape here. So what we would do, set up our triple integral. The z value, that's the most variable of the functions. So that should come first, right? It's got the most variables in it. So 0 to 1 minus x minus y, right? It's going to be of the function f of x, y, z, which is 5x minus 3y. dz would come first. Now it's really just a question of saying, all right, well, what are we looking at here for bounds for the y's and then the natural restriction for the x's? Well, the y's we know are going to go from the plane y equals 0 to really the plane of y equals 1 minus x. If you make that an extrusion into the z universe, then it would be going from 0, the xy plane upward, just following that path of 1 minus x. So we would have a natural 0 to 1 minus x. As long as we can restrict x, we'll be in good shape. All right. So it's really just a matter of saying, okay, well, what's the limit to what x can be? Well, if we're looking at this, well, it really seems like it would be the x-intercept of this line. Right. So where does this line go to 0? Right. So if I find the x-intercept, if I bring it down into 2 dimensions, y equals 1 minus x, just pretend that's y equals 1 minus x. You do it on Desmos if you want, but this is, not the hard part of the course, I don't think. We would be looking for the x-intercept because that's going to be this location here. When you think about how you find an x-intercept, we have y equals 1 minus x, set it equal to 0, and solve. So if you only restrict x so that it can only span outward from 0 to 1, we're restricting y so that it's capped off by that line, right? That's a function, right? If we restricted y so that it was capped off by 1 also, then we would create a rectangular region. But we're restricting it so that it's contained based off of that function, such that that function only goes from 0 to 1 in terms of x. Then we have the triple integral that gets the job done, right? The only thing I have to do is slap on a dy dx and we're good to go. All right. I meant to mention this before, but the word of the day is awesome. Awesome is the word of the day. I had it in my mind because I said it like 2 times within like 15 seconds. I'm like, this would be great to be the word of the day. And then I forgot. But here we are. All right. So I'm going to stop the recording.